Hi guys, and welcome to Calc Chats 27. Today we're going to be talking about the integral test with series, and specifically how to use improper integrals to solve to see if those series converge or diverge. So quick refresher, we're going to be going back into infinite series. So these are series from 1 to infinity. And we need to generally determine if they converge or diverge. And the tests that we've learned so far is the direct comparison test, the ratio test, and the nth term test. And so we know these tests probably not as well anymore, but we know that we can use them to determine if certain series converge or diverge. But there are going to be more complex series that we're going to come across that we'll need to use the integral test to solve. So this is the long definition of the integral test. So basically it says let an, all of those numbers, be a sequence of positive terms. This is very important, positive. And suppose that we can rewrite any term an as a function of f of n, where f is a continuous positive decreasing function of x for all x greater than n is any given positive integer. Then we know that the series from n equals big N to infinity of a sub n, and the integral from big N to infinity of f of x dx either both converge or both diverge. So we were talking about integrals and how they are similar to series. And so when we use the direct comparison test for integrals, that was just like using the direct comparison test for a series. And so we're going to use these improper integrals to kind of help us solve for these convergent series. Basically, it's saying that if we can rewrite our terms as a function, and we can find the integral of that function, then we can determine if the series converges or diverges based on if that improper integral converges or diverges. So we're going to go ahead and start on our first example. So we're given the series 1 over n times the square root of n, and we're asked, I should probably do this, does the series converge or diverge? So there's a few different tests that we could do. We could try to do a p-series test. We could try to do a comparison test. But we're going to go ahead and just use the integral test to help familiarize ourselves with the process. And so first we need to check number one, what would be my function anyway? And so we would imagine our function being 1 over x times the square root of x, or we could rewrite this 1 over x to the 3/2 because this is technically 1/2 and this is 2/2. Multiplying exponents, we add them, or we can rewrite this as x to the negative 3/2. So we have this function, let's just say 1 over x to the 3/2. Is it positive? Is it continuous? Is it decreasing? And the answer is yes, it is positive. There are no negative terms. It is decreasing. The terms are getting smaller. And it is continuous for our interval, because we are looking at x greater than 1. So it meets all of those conditions. So we can use the integral test. So let's first set up our integral. So integral from 1 to infinity of, I'm just going to keep this as a negative exponent, so it'll be easier to integrate, x to the negative 3/2 dx. And so I need to rewrite this as the limit as b approaches infinity as the integral from 1 to b x to the negative 3/2 dx. So now I can integrate this. So I take the limit as b approaches infinity, the integral of x to the negative 3/2, I add 1, so x to the negative 1/2, and then I divide by the new exponent, which gives me a negative 2. And we're going from 1 to b. Fundamental theorem of calculus, I can evaluate, so I'm going to write this as 2 over b to the 1/2, and then this is going to be plus 2 over 1 to the 1/2. And so when we evaluate this limit as b approaches infinity, this is going to go to 0. And so all that we are left with is 2. And so we know that the series n equals 1 to infinity of 1 over n root n converges. And it's an important thing to note. I want to kind of write this down here. The series does not always converge to the whatever you get for the integral. So when we actually go out and try to find, if we try to find the infinite series and we try to take partial sums, this would definitely actually be greater than 2 if you plug this in your calculator. So the series doesn't always converge to the same number as the integral converges to. Let's say same value. At the All right, so here is a DIY problem that I'd like you to try out. So you can pause the video, try to work through this problem. It's a very simple problem, the series from 1 to infinity of e to the 1 over e to the n. So try using the integral test to solve for the series, and I'm going to flip to the answer page in a few seconds. So our series does converge. I'll tell you the answer in case you don't want to look at all this work. But here is the work for evaluating this integral. And our series does converge. So now what I would like you to do is I would like you to try by yourself these 3 problems. These are not DIY problems. I'm not going to give the entire solution on this video chat, but we will be talking about them in class. And please try at least A. If you can't get through A, you know, kind of make notes of the questions that you have. If you can get all the way up to C, that is great. If you can't, that's also fine. Just try the 3 problems. I'm going to flip to the next slide, which is the answers. But again, I did not write out the full solution to this because I want to talk about these later in class. So take a minute to copy these down, try the problem, see how far you can get, and then make note of where your questions were and how far you got. And here are the answers, diverges, converges, and converges, and I wrote out what the integrals converge to. So this is it for Calc 27. Please make sure you come in with A, B, or C solved, and let me know what questions that you have. And as always, please like and subscribe.